Types of lava. Volcanoes come in many shapes and sizes. Volcanic eruptions may be quiet outflows of lava, which are so peaceful that one can stand close enough to toss in pebbles. Or lays, see in the figure. See how close she's standing to that huge-looking lava flow? Or they can be so explosively violent that they blow mountains apart and blast everything within 100 miles to smithereens. Not recommended for close observation. Both the shapes of volcanoes and the violence of volcanic eruptions depend on the same rather mundane thing, the physical properties of erupting lavas. The two most important properties of lava are its viscosity and the amount of gases dissolved in the liquid rock. Let's look at each of these separately. So you have 4 types of lava to describe. I'm going to read and help you figure out how to write these descriptions. In each description, you have to explain how the bubbles or water vapor content in the lava and how the silica crystals affect the lava and make it act the way it does. This one is low water, low silica. Let's see if there's any information here which can help us describe it. First, we have to know what viscosity is. Viscosity is a term that describes the fluidity or runniness of the lava. Some lavas are very runny, not quite like water, but more like warm honey or hot wax. When these lavas erupt, they flow for large distances before cooling enough to turn solid. You can imagine what kind of volcanic mountain you could make with runny lavas by thinking about, or carefully doing, pouring hot wax on a large sheet of paper. The wax spreads out into a large flat layer. Let it cool and harden, and then pour another layer. The second flow of wax will partly pond on the first and partly run off onto the paper to form another flat layer. If you keep pouring more and more flows, you will get a large but almost flat pile of wax. Therefore, many small eruptions of runny lavas form large, almost flat mountains like shield volcanoes. Eruptions of huge amounts of really runny lavas form flood basalt type volcanoes. So any lava that is runny is going to be, and I'm telling you what I'm going to read later, a low silica. Low silica makes runny lavas. Let's read some more and find out why. Other lavas are very pasty, like soft clay, and hardly flow at all. Imagine piling lumps of soft ice cream on a big, flat dish. You would end up with a tall, narrow pile. Likewise, pasty lavas form tall, steep-sided mountains like stratovolcanoes. And those are the ones that are the high silica. But more on that later. The viscosity of lava depends on several factors. One of the most important factors is composition, especially the amount of silica. This SiO2 is the chemical formula for silica, and it stands for silicon dioxide. Dioxide meaning 2 oxygens combined with a silica atom. Or quartz. Quartz is silicon dioxide. And this silica is melted in the lava. Silica molecules have the tendency to stick together to form long chains. These long chains literally get tangled together and make it difficult for molecules in the melt to slide past each other. This slowing of movement at the molecular level makes the whole lava less fluid, which means higher viscosity, because it doesn't flow like a fluid. It's more like a solid. A small difference in silica content can make a huge difference in viscosity. Lavas with about 70% silica, called rhyolites, are about 10 billion times stiffer than lavas with about 50% silica, called basalts. So 50% silica is like your low silica lava, your basalt, your flowing for long distances lava, like the Hawaiian Shield volcanoes. So anything with low silica is about 50% or so, and high silica is more like 60 or 70%, and those are like the Mount St. Helens ones. But let's find out more. The other important property of lavas governing the type of eruption is the amount of gases dissolved in the lava. And that here is shown by bubbles of water vapor, because the water vapor will expand when hot. The most important gases in lavas are water and carbon dioxide. Although water is a liquid at room temperature, it is definitely a gas at typical lava temperatures of 900 degrees Celsius, or 16 degrees Fahrenheit, to 1200 degrees Celsius, or 2200 degrees Fahrenheit. Very little gas can be dissolved in lava at the low pressures, around 1 atmosphere, which just means sea level, found at the surface of the Earth. We say the solubility of gases and liquids is low at low pressures. On the other hand, deep in the Earth where lavas are formed, the pressures are high because they're so deep underground, thousands to millions of atmospheres. That's a lot of pressure pushing down because of all that lava, magma, and earth crust on top of it. And significant amounts of gas can be dissolved in the lavas, so the deeper it is, the more gas can be dissolved, up to several percent by weight. We say the solubility of gas and liquids is high at high pressure, and that's a fancy way of saying the higher the pressure, the more gas you can dissolve in it. If we dissolve lots of gas in a lava at high pressure and high solubility, and then lower the pressure, which means as it comes up to the surface of the Earth, that's low solubility, the gas will undissolve or exsolve from the liquid to form bubbles. That's how it happens. It happens at the surface. So what happens to the gases in lava when it rises from the deep interior of the Earth to the volcano on the surface? Let's consider a couple of everyday examples. Look at a clear plastic bottle of soda pop that hasn't been opened or recently shaken. Most soda pop contains a few percent by weight of dissolved carbon dioxide. Even if you look carefully at the liquid, you can't see any gas inside. Remember, it's dissolved, except perhaps a few small bubbles and a tiny air pocket at the top. If you carefully open the bottle, many small bubbles quickly form and rise to the top and escape. If enough bubbles form, they take part of the liquid with them as a foam that flows out of the top. If you shake the bottle vigorously just before opening it, you trigger the formation of so many bubbles so quickly that the soda pop bursts explosively from the top, and you and everyone around you are sprayed with fine droplets of liquid. On the other hand, if the bottle of soda pop is left open for a long time, virtually all of the dissolved gas escapes, and no amount of shaking can cause the remaining liquid to spray out. It can only be poured out. And that is how a volcano can build up a lot of pressure if it's capped in. But if the cap is open and there's room for the gases to escape, the lava is just going to flow out. It is not going to explode. This shows the effects of dissolved gases. But what about viscosity? Think about making bubbles by blowing air through a straw into a glass of liquid. If the liquid is water, low viscosity, low silica. The bubbles you form escape easily. If you blow slowly, representing small amounts of escaping gas, low water, the water is little disturbed. Even if you blow vigorously, representing large amounts of escaping gas, high water, the water froths and bounces around a lot, but very little gets out of the glass. If you try the same thing with an ice cream soda or a malt, representing high viscosity or high silica lava, bubbles escape only with difficulty. You have to really blow. Even small bubbles bursting from a malt can get blebs of ice cream on your clothes. Blowing vigorously can launch the entire malt across the room. Starting to connect these? Different types of lavas show behaviors that are similar to our analogies of blowing bubbles in water or a milkshake. If an erupting lava has low viscosity, like water, that's low silica. And little or no dissolved gases, that's low water. Low silica, low water. The lava simply flows out of the central vent and spreads far and wide over the surface. Just like the low water, low silica figure. Draw that if you haven't already. If it has high viscosity, like a milkshake, so we're talking high silica, and no dissolved gases, low water, high silica, low water, the lava oozes slowly out to form a bulbous dome which hardly moves at all. See the low water, high silica figure. In either case, you could stand nearby in relative safety. These volcanoes are not going to erupt explosively because the lava is running. If the erupting lava has lots of dissolved gases, the gases come out of solution and form bubbles as the lava approaches the surface. If the viscosity of the lava is low water, the lava bubbles and froths a great deal right at the surface, tossing out tiny cinders and larger bombs of lava that quickly cool and fall back to the ground. This type of eruption, see high water, low silica, produces a spectacular fire fountain directly over the vent, usually resulting in a cinder cone. So that's how you get a cinder cone. Any remaining lava quietly flows away. So now you have an idea, and rewind this and listen to it again, of how to describe a low water, low silica lava and a low water, high silica one, and a high water, low silica, like this one, high water, low silica, which so many bubbles, so much gas in there, and it's going to froth and bubble out and make those little bombs. But let's look at the last combination. However, the last combination, lots of dissolved gases, high water, and high viscosity, high silica, is deadly. See high water, high silica figure right here. As the lava oozes to the surface, the gases quickly form bubbles that turn the lava into a red-hot froth that explodes out of the ground as a searing grayish cloud of superheated steam and tiny particles called ash, also known as cinders. The ash forms when the walls of the gas bubbles burst into tiny fragments. This type of lava causes explosive eruptions at volcanoes like Vesuvius and Mount St. Helens. So think of the high silica volcanoes, or lavas. It's hard to move. It doesn't move very much, so all the gases are trapped. And for Mount St. Helens, when the gas finally built up enough pressure, it built up so much pressure, it broke through a mountain of rock. That's huge. Huge. Okay? So you might need to rewind this if you're trying to understand these types of lavas and how you can explain them.